Hello, my name is Dr. Erin Griffin, and today I'm going to be talking about ambient obstruction solitons and homogeneous gradient box solitons. So I'm going to start out by kind of reiterating these things that I said in my introduction video and just kind of talking about what each of my videos will talk about, and then we'll get going into this first part of the talk. So in part one, in this video, I'm going to be talking about general geometric flows. What I mean by that is, well, I'm going to be talking about geometric flows in general, motivating them, why do we care about them, but I'll also be defining kind of a new object for a lot of us, which would be a geometric flow for a general tensor, Q. Okay, and I'll talk more about what that means in just a few minutes here. But in part two of the video, what I'll do is I will look at the case where we have the ambient obstruction tensor be that tensor Q. Okay, so I'll be investigating ambient obstruction solitons. I'll also discuss and define the ambient obstruction flow, and again, go through some results and talk about the methodology that we use to get results for the ambient obstruction tensor. And then lastly, I will be talking about the Bach tensor, which is a specific case of the ambient obstruction tensor for dimension 4. So again, I'm just going to be narrowing my scope throughout these three talks, so that part 3 will be the most specific, looking specifically at dimension 4 with that its own specific methodology and some much more robust results than we get for parts 1 or 2. All right, so getting started, let's kind of talk about some of the tools we have in geometry. What is the motivation of geometry? So geometry broadly we think of as looking at how things are shaped and dealing with shapes. And what does this mean? So one of the tools that we're going to need to do this is we're going to need to consider a metric, right? A metric is a way to measure distances and angles. And for our purposes today, we can think very much like an inner product, right? For an inner product, if I'm looking at some vectors v and w, if I take their dot product, I'm looking at their norms multiplied times cosine of the angle in between them. So it would give me the angle between those two. And if I look at a vector dotted with itself, that's just going to give me the norm squared of my vector. A metric is just a much broader way of doing this. Rather, an inner product would be kind of a specific example of a metric. Okay, so a metric gives us a way to measure things. And as I'm talking about this, some of the verbiage I'm using would suggest that there are multiple types of metrics. There's a lot of different ways to consider it. And this kind of brings me to one of the main ideas in really geometry as a whole, but specifically in Riemannian geometry, we are wanting to find, let's say, the best metric. The word best is pretty vague. I'm going to leave it that way intentionally. But that's kind of going to be the guiding principle for this talk, and it's going to motivate a lot of what we do. So when I'm looking at metrics, and with this goal of finding the best metric, I'm going to start by limiting myself to a specific type of metric. That is, I'm going to look at Riemannian metrics. So these are positive definite metrics. So for non-zero vectors, the norm squared of that vector is positive. Okay, so Riemannian metric is just a specific, nice kind of metric. And again, it is just a way to measure things. And as Riemannian geometrists, we've decided we want to look for a best metric. We think it's going to be Riemannian. Let's stick to this specific type of thing. Okay, there are plenty of non-Riemannian metrics, but I'll save that for someone else for another day. Moving on, we want to consider different types of objects, and the object that we will consider is a manifold, a Riemannian manifold specifically. So that's going to be a manifold M paired with a Riemannian metric G. Again, really, we're saying, think about this as a nice surface, like a sheet of paper or a piece of fabric. They are surfaces that behave like you think that they would, broadly speaking. Okay, and so a surface would be a two-dimensional manifold, as you may know, but we can also look at 3, 4, 5 n-dimensional manifolds, all just the same. Okay. Moving on, another specific type of Riemannian manifold is going to be a homogeneous manifold. Okay, again, we're trying to say, like, what are some really nice cases that we can look at as we are trying to start finding things. So a homogeneous manifold is going to be a Riemannian manifold where there's an isometry between any 2 points. I can switch any 2 points, and those 2 points won't know that anything happened. They look the same around those 2 points. So a very, very good basic favorite example maybe would be a sphere. I can take any 2 points on a sphere and switch them, and around those 2 points, everything looks the same. Really, what this boils down to, or one of the main ways we see it manifest in my work, is that these manifolds have constant scalar curvature. Okay, so what is curvature? Well, curvature generally, I'm going to be representing it using the letter Q. So curvature, let's say, is a tensor that essentially measures different aspects of how unflat a manifold is. Okay. How unflat, how much it differs from a plane, okay, or hyperplane or what have you. Okay, so I'm going to talk about this generally using Q. So again, to summarize, my goal is to find a metric or my best metric, and I have these tools and objects. I have the curvature that's going to tell me how curvy something is. I'm going to be looking at the curvature of a Riemannian manifold, and that manifold is endowed with a metric. Okay, now, one of the ways that we like to approach this question of finding the best metric is using a geometric flow. So a geometric flow is going to be a differential equation in which the metric, g of t, is going to be changed over time in accordance with our chosen tensor. So for a general tensor Q, we would define our Q flow as the one parameter family of smooth metrics G, such that my initial metric is H. And as I change my metric G with respect to some variable T or with respect to time, it's going to remain in equivalence with the curvature, right? So some really common, or some of our favorite flows would be something like the Ricci flow, which is going to be the case where Q equals -2 reach. And then today we're going to look at the ambient obstruction flow, where Q is equal to my ambient obstruction tensor, and the Bach flow, where Q is equal to the Bach tensor, right? Really what I am doing here in setting up a Q flow is setting up a dummy variable Q to be like a box for me to plug in other tensors down the road, right? And I'm going to give Q certain properties that I want, so that I can look at other specific tensors with that property later. Okay, so that's kind of the setup. Now you might be thinking, how does this help us? Well, in developing a differential equation to model or to give us some notion of what's happening, what we have done is given ourselves all of the tools that come with differential equations. One of the main basic things that we might do with a differential equation is look for fixed points. Okay. So in terms of geometric flow, what this means is looking at solitons. It's going to be the word that we use for that. Okay. And so I have some equations here, but before I get to looking at a normalized Q soliton, let's talk about what this is kind of heuristically. So if you think about a geometric flow kind of like a stream, a soliton would be like a rock that sits in the stream that is self-similar as the stream erodes the rock. So if you started with a spherical rock, as the stream tumbles and moves the rock, it stays as a sphere and just gets smaller, or maybe it collects other particles and becomes a bigger sphere. Okay, but it stays a sphere the whole time. Okay, so I like to think of solitons and how they relate to flows as the soliton is a rock, and the flow is the river or stream that that rock is sitting in. Okay. Mathematically, how do we look at this? How do we consider these things? Well, a soliton, or really more specifically a normalized, I'll talk about that in a minute, a normalized Q soliton is going to be any metric G that satisfies the equation 1/2 times the Lie derivative for vector field x of G equals CG plus 1/2 times Q. Okay, so again, my soliton is the metric that satisfies this broader equation. I'm going to pick a vector field and I'm going to leave Q here again as kind of a placeholder for a tensor that I might look at later. Okay. Well, that's broadly what solitons look like. Again, if I'm investigating something new, I'm going to want to narrow down the things that I'm looking at. And so I'm going to be only focusing my attention on gradient Q solitons. Okay, a gradient soliton, all that means is that for my vector field x, I'm going to be looking at the gradient of some function f. I'll call f my potential function here, but when I plug in gradient of f for x, I see that this Lie term just becomes Hessian of f. And the Hessian is what we know and love from multivariable calculus. It is that matrix of second order partial derivatives. It's the same Hessian of our multivariable function f. And then it's still going to be the same thing on the right-hand side. Now, I mentioned this word normalized. What I mean by that is I've included a 1/2 in front of the Q. Now, this is an important coefficient when we are looking to show how solitons relate to the flow, and in the proof that I do in the corresponding paper to this talk. So I've chosen to normalize the soliton in this way, but you'll see that this changes depending on the flow, roughly. Okay. So we have this idea of a gradient Q soliton. Normalized just refers to this 1/2 here to give us some specific verbiage. F is our potential function. And then we're going to say that our solitons are going to be one of three things. They're expanding if my constant here, C, or here also, if C is positive, or C is negative rather, our solitons are expanding. If C is equal to 0, our solitons are steady. And if C is positive, we'll say that our soliton is shrinking. And this convention can change a bit from paper to paper. Again, it depends on which side of the equal sign that term is on, lots of different things. So if you're reading literature that is related to geometric flows, just be wary of how shrinking, steady, and expanding are defined. But for the purposes of my talk and my paper, this is how I will define them. Okay. So we have this idea of a Q soliton. Let's look at one results for how this might play out. So I'm going to let MG be an n-dimensional compact soliton to the Q flow. So I'm already assuming that my manifold is a soliton. Then these three things follow. We'll see that B follows from A and C follows from B, with some additional assumptions about our tensor Q. But let's look at A for a minute here. What I'm asserting is that the norm squared of my Lie derivative and the integral thereof is equal to -2 times the divergence of my tensor Q. Okay, so let's look at how this is proved, and then I'll talk a bit more about B and C, because I think that those are really the more interesting terms or interesting parts of this lemma. So to prove A, the first thing I'm going to do is I'm going to do a little bit of reorganization, a little bit of housekeeping, and I'm going to move my CG term over to the left, and I'm going to multiply everything by 2. So really, I'm going to consider a Q soliton. That's what I've assumed. And I'm going to let Q equal the Lie derivative minus 2CG. Again, all I have done is take my equation that I know my manifold satisfies, and I've reorganized it. I'm going to take the divergence of each side. So get divergence of Q equals divergence of each of these. The divergence very much behaves like a derivative, especially with regards to multiplication, addition, subtraction, things like that. So I take the derivative, or I take the divergence of my Lie term and the divergence of my metric. And I see that this term goes to 0 because the divergence of the metric is 0. And so I'm left with the fact that the divergence of Q equals the divergence of my Lie derivative of G in the direction of X. we know, again, this is a math fact that I proved more thoroughly in my paper, but we know that the norm squared of our Lie derivative, well, that's the inner product of the Lie derivative with itself. There's a specific property that takes us from this inner product down to looking at it as the difference in divergences with this function I sub x. And I know from above that the divergence of my Lie derivative is equal to the divergence of q. So I'm able to see that the norm squared of my Lie derivative equals, well, the norm squared or equals 2 times the divergence of this function I sub x of my Lie derivative of g minus 2 times the divergence of q. Again, have I placed any assumptions on q? Not yet. This would apply for any tensor q, okay, and for any q soliton. So I see that I have this fact, and so now I'm able to quickly integrate over my manifold M, and note that since M is compact and has no boundary, by assumption, that the integral of my Lie derivative of the norm squared is equal to, well, the norm squared was equal to that. I'm able to split up my integral, and I see that because M is compact and has no boundary, that this first integral is in fact 0. So I'm left with the fact that the integral of my Lie derivative equals -2 times integral of the divergence of q, as I posited in the beginning. Okay, so there's a lot of hand waving in that. There's a lot of different, calculations and stuff that go into this that I'm not going to go through for the sake of time. But we get this fact. So now what? Well, so far this applies to any q. So let's look at what happens when we let q be divergence free. If q is divergence free, that means that the divergence of q is equal to 0. So what I see is that, well, from part A, I know that this term on the left equals this term on the right. But since q is divergence free, this term equals 0. So consequently, I get the integral of the norm squared equals 0. But what this means is that my Lie derivative itself equals 0. And consequently, x is a Killing field. So again, from part A, not super useful on its own, but now once we place an assumption on our tensor q that it's divergence free, we learn things that have to be true about our vector field x. We learn things that have to be true about our Lie derivative. But what's more interesting, let's place another assumption on our tensor q. So suppose that q is both divergence free and trace free. We know that from B, because q is divergence free, we can apply that. So we know that our original equation for the soliton can be transformed into q equals -2cg. Why? Because our Lie derivative term equals 0. So I know that q is equal to -2cg. Taking the trace of both sides of this, since q is trace-free, I get 0. And I see that the trace of, well, -2c stays the same, and the trace of g equals n. So I see that 0 equals -2nc. We know that n is the dimension of our manifold. So n is obviously greater than 0. And what this forces is that it forces c to equal 0. So we know two things now. One, c is 0. So we can say that our soliton is steady. Another thing, since q equals -2cg and c equals 0, that's going to be -2 times 0 times g. So q is equal to 0. And so from this, we see that our manifold is Q flat. Think back to a few slides ago. We had talked about Q as being kind of our general measure of curvature. If something has zero curvature, regardless of the measure, it would be flat in that regard. So if I'm saying that Q equals 0, that means that our manifold is Q flat for whatever that Q is. So this has kind of given us an introduction. We will use this very lemma in the next part of the talk. But I'm going to take a break and stop the video so that you can take a break as well.